Okay, so our next speaker is Nicolle Gonzalez, and she'll tell us about the higher structure of Heisenberg and Clifford algebras.
Hi everyone, thanks for coming. I know it's a beautiful day, it's hard to be here. But anyway, so in the previous talk, Alexander very nicely introduced a little bit of what I wanted to actually talk about, right? So at the end, he mentioned something about this boson-fermion correspondence, which you'll see will play a part towards the end. And he started talking about these Heisenberg algebras, right? So just a little bit of motivation. One of the things that, if you're a representation theorist, you want to do is understand, obviously, classified representations, right? And in the context of infinite dimensional Lie algebras, that's a very hard question. It's something that people don't really understand very well. If you look at affine Lie algebras, however, there's a construction known as the Frankel-Segal construction, where the idea is that if you start with some affine Lie algebra, right? So the usual presentation. Let's just define it like this for now. Then this thing has a natural subalgebra known as the Heisenberg subalgebra, which is essentially, let me define it correctly. This thing. Where this is your Cartan, the Cartan subalgebra of your Lie algebra. And their theorem says, well, you know, if you start with the basic representation of your affine Lie algebra, that representation actually decomposes as a sum, as a direct sum of the irreducible representation known as the Fock module for your Heisenberg subalgebra. And you can extend the representation for this one, for the Heisenberg subalgebra, to a representation of the full affine Lie algebra using vertex operators, right? So in words, that's basically saying if you take this representation, you can decompose it as a direct sum over modules, and the action of your Heisenberg subalgebra here can be extended to a full action of your affine Lie algebra here using vertex operators.
And what is B? I missed.
Here, so this is the irreducible highest weight representation, or the basic representation for G hat.
With some weight?
Yeah.
With some highest weight?
Lambda 0. Yes. And so looking at this construction, it's not what I'm actually going to talk about, but looking at this construction, you might ask, well, are there other representations that arise in this way? Can we construct representations for more complicated algebras by starting with a Heisenberg subalgebra or Heisenberg Lie algebra, right? So in our context, we're going to do an analogous construction, but rather than using this Heisenberg algebra, we're going to define a different one, and we're going to induce that, or from that construct a representation of the Clifford algebra, and then categorify. So that construction, well, for that I need to first define the Heisenberg algebra that we're interested in. So, definition. So we're going to define our Heisenberg algebra as the associative unital K algebra. And so here, for all intents and purposes, we're going to set K to be a field of characteristic 0. So it's the associative unital K algebra generated with generators. We're going to call them Pn and Qn, or M for N and M in N, and relations given by the following. So we have the commutator relations, so the P's commute with themselves, the Q's commute with themselves, and then we have the following relation between So you look at this, and if you're familiar with Heisenberg algebras, you might think, well, this looks really weird. These might not be the usual commutation relations that you're used to. And the reason for that is that secretly, I really should have written z here, and I really should have said this is the integral Heisenberg algebra, right? Namely, that is just because we want to eventually categorify this, and we want our generators to be an integral basis, right? So the usual presentation, right, and also has generators given by let's call them alpha n and alpha minus n. It has this commutation relation that was written in the previous talk, right, where this is given by n times delta n minus h bar, where this h bar is essentially a central. It's central in the sense that it commutes with everything. Yeah. Okay. Great. And it's sometimes known as the charge of your Heisenberg algebra. Cool. So using this.
Sorry about this notation. What is e to the power n minus k means then?
Oh, sorry. No. I changed notation. Sorry. N minus k.
Ah. Okay.
Sorry.
Cool. How is the old presentation related to the new one?
How is the old presentation? Yeah, that's a great question. So I can write the equation for you, and it's not going to be very exciting. But essentially, if you know the relation between power sum symmetric functions and elementary and complete symmetric functions, that's exactly the relation between these. These act like power sum symmetric functions. These are your elementary and your complete symmetric functions. Yeah. So actually, there's an alternate presentation here where we can instead label them by 1 to the n and q1 to the n. And this is related to the fact that they're essentially acting, as you will see in a little bit, on the ring of symmetric functions, like complete and homogeneous symmetric functions. Or sorry, complete and elementary symmetric functions, right? And these generators will satisfy essentially the same commutation relations. Great. So, oh yeah, well actually I'll tell you right now. So this is a theorem, a proposition, however you want to think about it. So the ring of symmetric functions is an irreducible representation of this Heisenberg algebra whenever, if and only if, let's say, h bar is actually non-zero. Right? So if you look at this presentation, we want h bar to be non-zero. For our purposes here, we're actually setting h bar equal to 1. What is the action here? So one of the things that we see from this presentation, actually, is that we can define an action on the ring of symmetric functions by setting alpha n to basically be a differential operator, right? So we set alpha n to act by differentiation. Let's say, do it when I use Pn. I guess I shouldn't have done that, but I'm gonna write Pn. Huh?
Just write out power.
Yeah. Good idea. Yeah. And then I'm going to write minus n to act by multiplication by the nth power symmetric function. Sorry, I want to write Pn, but if I write Pn, it'll be confusing with this, which is why I'm purposely not doing that.
Sorry, those are the generators of your ring of symmetric functions.
Yes, that's exactly what it is. Yeah. So here, sim is
Can you just
basically.
give them separate names? Y instead of X?
Sure. It's just, I don't want, yeah, let me do that. We call it yn and multiplication by n times yn.
Great.
Or this is y1, yn, blah, blah, blah. And each of these, this is the n. Yn is the n power symmetric function. Sorry, normally it's denoted Pn, like I was saying, but there's too many P's and Q's in this entire story, so it's kind of confusing. Okay, so we have this action, and you might ask, well, how does this action what does this action mean at the level of these other generators, right? Yes.
The alpha n, what does this mean? Delta, like a delta y.
Ah, okay, sorry. So I want to, I'm claiming that the ring of symmetric functions, that my Heisenberg algebra acts on the ring of symmetric functions, right? And I want to explicitly define what the action is going to be. And what I'm saying is, if you take the ring of symmetric functions to be, the usual polynomial ring, but in variables, I'm going to call them y1 through yn, but really you should think of these as power sum symmetric functions. Then, if we define the action to be differentiation with the nth symmetric function and multiplication, this induces an action of the Heisenberg algebra in this space. And if we take h bar to actually be any non-zero integer, it's an irreducible representation. As the Fock module or the Fock space representation, or however you want to denote it. At the level of these generators, right, we see that Pn is actually going to be acting just by multiplication by your nth, this is your nth homogeneous symmetric function, right? Qn is going to be acting by, or I don't want to say multiplication actually, let me just say, it's going to act by Hn. This is going to be acting by Hn perp, and I'll define what that means in a second. P1n is going to be En, and Q1n is going to be acting by En perp. So here the perps are denoting the adjoints with respect to multiplication, the adjoints of multiplication with respect to the Hall inner product, right? So just as a reminder, if we, so f perp, given f in the ring of symmetric functions, f perp is the adjoint with respect to the Hall inner product. Where this is the Hall inner product. Right? Okay, great. Right, so another way to actually view what this is just to note that we can decompose this as a vector space into two different pieces, where this is the stuff that's generated by, let's say, the qn's, and this is the stuff generated by the pn's. And then we can actually show that this ring is nothing more than the induced module from H plus to H minus, to the full Heisenberg algebra of the trivial representation, right? So if you set all the q's to act by 0, and then you just induce up to the full representation, the full Heisenberg algebra, then you actually recover precisely the ring of symmetric functions. And this space is what we're going to be calling our bosonic Fock space. Cool. So now, with the setup, what our next step is going to be is to actually categorify this. So, just for the sake of clarity, right? Previously, Tina talked about the Grothendieck group and how, one of the conditions that you imposed was this exact sequence, or this exact sequence condition. So for us, we're going to be talking about the split Grothendieck group, which I'm just going to remind you what it is for the sake of clarity. Right, so we're going to basically say if we have some additive k-linear category, then we're going to define k0 of C as the abelian group generated by the classes of objects, right? Where X is an object of C, and we take the relations that X and Y is just split this way, right? And obviously, if our category is also monoidal, then our tensor product descends as a product, right? So this is just so that we're all on the same page, especially those of you who may not have seen this before. And then if our category is graded, we also have a grading shift. A grading shift just means we have some sort of grading shift outside as well. And then lastly, if our category has some sort of homological grading on it, then the grading itself will also descend, but instead as a negative sign, right? So use curly brackets for homological grading, right? Then this is just going to be minus 1 to the r of the object x. Great. So using this setup, we have the following definition. So we're going to define H prime to be the category, to be the additive bilinear category, monoidal also. Monoidal category with objects given by sequences with objects generated by upwards and downwards arrows. So these are, let's just say we can have direct sums, finite direct sums of sequences consisting of upward and downward arrows. And then the morphisms are going to be planar diagrams that respect the orientation and are read bottom to top, right? So modulo the relations. Well, first of all, isotopy. That's to say, we can wiggle the diagrams and be fine. And the following. So if you have two strings going upward, you can untangle them. Then you have an in-string relation, right? Then we also have, what if they go in the other direction, up and then down? One and this probably 0. Okay. So why are these relations cool? Well, first of all, if you look at this, and you notice that if you set this, if you think of this as just SI, i.e. a transposition on I on the ith strand, this is telling you that these are just SN is acting. Actually, I can even say more. KSN is acting on the endomorphisms over H prime of, upward strands and upward strands. Then you look at these relations, and actually, you might ask one thing. Well, I have a right twist girl, but what about this? What is this? Turns out that this is actually a very interesting object, which we're going to, for the sake of drawing it, denote it by a dot. And using these relations, you can deduce, or you can derive, whatever, that this dot actually satisfies the following relations. Right, so these are known as just the dot sliding relations. Right, so these, together with the SN relations, actually tell us that that there's an action of the degenerate affine Hecke algebra, again, on the endomorphisms of, n upward strands. Right? So I didn't define this, and I don't think anybody did in Monica's talk or anybody, but just for completion, right, here we're thinking of, this has polynomial generators, which we can view as the dots, and then it has symmetric group generators subject to the same relations as the symmetric group, right, which are basically the crossings, and these relations are precisely the relations that define the polynomial generators with the symmetric group generators on them. Why am I telling you this? Well, because one of the things that you might say is, well, we have this algebra, why is it why is the Heisenberg algebra interesting? Another question. Why is the category interesting, right? Why would you want to go through the process of constructing all these weird diagrams when are they even telling us anything else? Well, for starters, not only do we have an action already on of the group algebra, the symmetric group, we actually have an action of the degenerate affine Hecke algebra. So this is more structure that you would have seen by just considering the algebra. So that alone, the fact that it has interesting endomorphism rings, serves as motivation for why you might want to do something like this. So actually, we have the following theorem. Yes.
You might want to find that those first two ones you got to be, they're all down arrows. You also have.
Oh yes, of course. Yeah. So actually, as a consequence, from here you can actually derive that these same relations, all the ones that hold for upward strands, hold for downward strands. So you can basically just rotate any diagram and get the same relations. Yes.
Sorry, I must have missed this, but with the degenerate affine Hecke algebra, how do the polynomials actually add dots onto the diagram?
Yeah, let me just define it. So this you can think of as having generators. We call them S1 through Sn minus 1. These are the usual symmetric group relations, right? And then you have some polynomial generators. 1 through yn. Did I get the numbers right? Yeah. Right. And these, so the relations between these two are basically that yi. I mean, I can read them off over here, but for the sake of. Oh yeah, sorry. And these are polynomial generators. So these go to the crossing, and yi gets sent to a dot on the ith strand. Yeah. So here you can just read the relations directly. Great. Oh yeah, so I was going to tell you a theorem. So this is a theorem due to Khovanov that the endomorphism, I think everyone can see here. The endomorphism ring of taking n upward strands is actually isomorphic to the degenerate affine Hecke algebra tensored with and here I really do mean just a polynomial ring, not the ring of symmetric functions. This is just a polynomial ring. Great. Why? Where did this come from? Right, so when you're looking at these diagrams and saying, all right, I have n upward strands on the bottom, n upward strands on the top. Hopefully you believe me that, at least the Daha makes, or the degenerate affine Hecke algebra has something to do with it. But the other thing that you have to consider is closed diagrams, right? Bubbles that are floating in between, right? Diagrams like this that can just be stuck between any arrows or any place in the picture. And there's these rules that allow you to basically slide bubbles through it so that you can get all the bubbles on one end when you decorate them with certain dots, right? Because you can have diagrams that have dots on them, and you study that endomorphism algebra, you actually find that the endomorphism algebra of those diagrams is nothing more than a polynomial ring, which is why you look at this.
But this is central only on the parameters 1 and 2.
Sorry, what is central on what?
The bubbles that just commute only on the parameters.
I'm not saying that they commute. I'm just saying that there are rules so that you can push all the bubbles, modulus certain relations, all the way to one end of the diagram.
Yeah,
That's all I'm saying.
In Khovanov's paper, it's degenerate case, right? Like parameter 0, 1.
The parameter for
The Heisenberg.
oh the h.
Yeah.
H bar is 1. Yes, I said that at the beginning. Yeah. Yeah, this is the most simple case, right? I'm not dealing with. No, but if the parameter is not 1, you still Yeah, so I guess, what are you? Okay.
The bubbles are always there.
Like, the bubbles are always there. They're not going away. But...
Is this as an algebra or as a vector space? These different possibilities.
This is as a vector. No, it should be as an algebra, I think. Yeah. Okay. So,
That was the question about whether they're central. These bubbles with dots are actually central?
the bubbles with the dots are not central. So I'm just saying there are relations that you can derive that allow you to push all the bubbles to one side of everything. Oh no, then this should be as a vector space. Sorry, forgive me, obviously. Yeah. This is a vector space. No, it's an algebra. Otherwise it doesn't make any sense. Yeah. Okay, great. So we have this construction, but this isn't Khovanov's Heisenberg algebra. This is what you build Khovanov's Heisenberg category out of. And the reason for that, for what we're going to do next, comes precisely from. Huh?
It is as an algebra.
Is it?
Yeah. It
But
doesn't.
the bubbles
hold
don't. Generally, the bubbles don't slide.
Not in K theory, but when you're stacking vertically, they do.
Yeah, but not horizontal. Oh.
Yeah.
I guess you
Yeah,
first
that
move them
composition
and
is
then you
vertical.
view them up. Okay, that's a good point. Alright.
So you're saying you can move them to...
You can move them vertically, and I was thinking of moving them horizontally. I'm like, you can't move them horizontally, but you can move them vertically, of course, because they just shuffle through.
And then once they're off to the side...
Once they're off to the side, then
they're
it doesn't
central.
matter. Yeah. Thanks for clarifying that. Yeah. Okay, so then this path right here tells us the following, right? It tells us that PSN, in particular, lives inside here, as we just argued, right? So, what are some of our favorite elements that live here? Well, how about Young symmetrizers, right? So if we look at Young symmetrizers, we might ask, well, what is the image of these Young symmetrizers here? We get nothing more than what we're going to call Young idempotencies. And we would very much like to make this part of our story. So that motivates the following definition, which is actually Khovanov's Heisenberg category. H is defined as the Kirby envelope of this category H prime. Right, so just as a reminder, what this means is that the objects here of my actual category are going to be pairs of objects. Let's call them X and E, where X is an object in H prime, and E is an idempotent. So E is an element in the endomorphism, right, of H, such that E squared equals E. Right? And obviously the morphisms in this category are just going to be maps between the objects that commute with or make the diagram commute with respect to the idempotents, right? Cool. So in particular, we want to denote objects, very special objects. We want to denote by P the object with the identity idempotent. We're going to denote by capital Q the downward object, again, with the identity idempotent. And following from here, this actually allows us to define for every single lambda, for every partition, a unique, or unique up to equivalence, right? Object, which we're going to denote P lambda to be precisely n strands with the idempotent, the image of the Young symmetrizer in our endomorphism algebra. These objects we're going to denote by a box lambda on upward strands, on n upward strands, right? So, for example, and some special partitions are where lambda is a row or lambda is a column. When lambda is a row, we actually denote, so for example, if lambda is 1 to the n, right, and this maybe harks back to the notation that I had previously, right, we want our box to be, we're just going to denote it by a shaded box labeled n. And then when this is a column, I'm going to do this backwards. Row. Yeah, I might have done this backwards, sorry. You're at column. And row. When lambda's a row, then our partition is just going to be denoted by a white box. Labeled n. Okay, so as an example, for example, when n equals 2, our C2, for instance, right? So this is a partition with 2 rows. This is going to be given by 1/2 times the identity plus the partition 1, 2. Another partition, the permutation 1, 2. And this gets taken under our identification to 1/2 times the identity plus a crossing. And this is what we define to be the object P2. Alright, so for an anti-symmetrizer, i.e. when this is you might say, well, why on earth do you know that this is the right category? You know, and obviously, not only is the structure interesting, but it actually gives us exactly what we wanted. So we have the following theorem due to Khovanov and Brundon, Savage, and Webster. This is from 2010 when the original paper came out, and this is actually like a few months ago in December 2018, where they finally showed that if you take the growth and decrease of this category, of Khovanov's Heisenberg category, you really do recover the integral form of the Heisenberg algebra. So for years it was known that this surjected here, but the fact that they're actually the same was very recent. Cool. So this is part of it. We have the algebra, but another thing that you might want to ask is, well, what about the action, right? We need not only categorify the structure of the algebra itself, but also what it's doing on the ring of symmetric functions. And for that, we need the following theorem, Heisenberg, from like the 1960s, where he basically tells us that if we take K0 of the category of ASN modules, then this is nothing more than the ring of symmetric functions, right? And this is essentially just achieved by taking the Frobenius character map, right? Where induction and restriction on this side coincide with the usual structure here of the algebra, so co-multiplication, multiplication. In using this, we can define the action of our Khovanov's Heisenberg category on so acts on precisely this, right? And they do it by basically, you can set P, right, to be an upward arrow, and if we can think of this as labeling the regions now, so we're going from n to n plus 1, this is nothing more than inducing the induction functor going from ASN mod to KSN plus 1. And in the analogous way, we can view Q as going from n plus 1 to n as being nothing more than restriction of U. The analogous story of this is n plus 1 and this is n. Right, so in this way, we actually also recover precisely the same action that the Heisenberg algebra had on the ring of symmetric functions, that category. So, oh, I want to point something out, just to tie it back to something that Monica said previously. One of the relations here, yeah, good, I still have it. this one, erase everything. Right? This relation, if you parse it and you think about what it's saying, well, it's saying we're starting with QP. I don't know if anybody can see it. Let me just rewrite it. Right, so we're starting with QP. Somewhere in the middle, we end up with PQ. And here we go again to QP. Right, what is this? This is PQ, ends in PQ. And then here we go from PQ to the identity to is that right? Did I draw
Bottom is QP.
This should be Q. Yeah, this should be PQ.
Q goes down.
Oh, thank you. Yeah.
And the one to the left also.
Oh.
And the one in the middle is also.
I'm like so I'm like way too close to the sorry.
Before that there's PP. You wrote PP on the straight line.
Yeah.
It's a straight line.
The middle pair.
The middle wow, sorry. I'm like, oh,
just
that
one
sounds
person
so
should say the
Yeah.
correction.
Yeah.
There.
Oh, yeah, okay, thank you. Wow, that was really weird. Yeah, okay, great. It should all be QP, of course. Okay, what was I trying to say? That one of the relations here, what this is telling you, is that this isomorphism holds in Khovanov's Heisenberg category, right? And if you step farther away from it, and you can actually read the diagram, which I can't this up close, and you read it bottom to top, right, you'll realize that these maps are just giving you the two pieces that take you from QP to the decomposition, and then the composition backwards from PQ to QP, and from the identity to QP. And if you look at this, right, and you think about the fact that Q is supposed to be a restriction functor, P is supposed to be an induction functor, and vice versa, this is really just telling you restriction composed with induction is supposed to be something about induction and then restriction, right? Some sum of induction and restriction functors. And what is this? Did I get it backwards?
Induction. We have restricted induction and restricted induction.
Oh my god. Thank you. Induction, restriction. Yeah. And if you look at this, this is nothing more than a special case of the Mackey formula that Monica mentioned previously, right? So actually, if you think about, well, I have this algebra and I want to just construct the category from scratch, just knowing this and just thinking about the fact that what you're trying to model is nothing more than induction and restriction functors, you could literally just come up with a category yourself. It's very, very natural. Cool. Okay, so enough about this.
At least if you're Khovanov.
And you're Khovanov, no small b. No, but it's not a weird thing to come up with. That's what I'm trying to get at. Okay, so this is the Heisenberg category. How exciting! But at the beginning, I told you that we would be talking about this Clifford story as well, right? And in order to do that, I want to remind you of something, right? So we have this. We have Heisenberg algebra is acting on the ring of symmetric functions, which is essentially just telling us, all right, this Heisenberg category is acting on this category of modules. Great. Now, we would like to construct an analogous picture to this Frankel-Segal story, where starting with a representation for H, maybe we can build something more interesting, right? Namely, if we take a direct sum, and let me give Sim a name. Let me call this F. No, let me call this B. No, never mind actually. Sorry, I got the straight from my never mind. Let me write this. Right, so let me consider this space, which is nothing more than just a bunch of copies of the real symmetric functions glued together and TWC is just a parameter to keep track of what level I'm on. My question is, well, is there some sort of algebra that also acts on this space, such that maybe through some way we can induce the action from H to the full algebra? And of course the answer to this is yes. Turns out that something known as the Clifford algebra acts on here. And the relation between that is given by a theorem due to Fock and Frankel using vertex operators. So that's what I'm going to explain in the remainder of the talk.
So do you want your sum to be over T and Z or C and Z?
C and C. My God. Thank you. The amount of typos are awful. Yes. Thank you, Monica. Okay. Cool. What do I want to say? Yeah. So we have the following theorem. I'm going to write it out and then I'll explain what it's actually saying. So we have the following theorem. Tells us that. Yes. Is that how you pronounce it? Siegel? Oh, thank you. Okay. I have typos and I don't know how to read names. I'm sorry. Okay, so cats. So the operators psi and psi star induce, and I'll define these in a second, induce an action of the Clifford algebra on this space. Let's call this space B for bosonic Fock space. B where psi is going to be defined in the following way. So psi z is going to be an operator, e to the alpha naught, e times the exponential of fine. Okay, so what's going on? So there's a theorem and it tells us, alright, that if we define these two weird looking operators and we act on this bosonic Fock space, right, which is really just a bunch of copies of the ring of symmetric functions, then actually we can induce an action of the Clifford algebra. So several questions. First of all, what does it mean to be a Clifford algebra? Well, let me define that here. So here, for our purposes, our Clifford algebra is going to be generated by psi I and psi I star modulo the relations that psi I, so I'll just write it out, psi I psi j plus psi j psi I equals 0, the same relations for the starred version, and the mixed commutation relation or anti-commutation relation. Right. So, given these operators, the theorem is that, well, actually these operators satisfy these relations. And I'm kind of lying a little bit here, but that's morally what we want to say right now. So what are the stars everywhere in the second one? Yes, of course. Okay, so then morally, sorry, not morally. So what is this actually saying? So what is the C alpha naught? To erase some things. So here, remember remember that if we take a TCF, let's say in TC symmetric functions, the C alpha naught is doing nothing more than just reading C we can think of as a charge. Right, so this is nothing more than Z to the C of F, so it's just going to read off the charge or the level that we're at. And these alpha n's and these alpha minus n's are just the generators for the Heisenberg algebra that we saw previously, right? Not the p's and the q's, but the usual generators. Right? So what this is telling us is that just by knowing how the Heisenberg algebra is acting on each of the pieces, we can actually induce the full action of the Clifford algebra to this big space, right? These objects right here, this nasty form here, well, I forgot, this should be an exponential, sorry. Exponential. It's two exponentials. These things right here are precisely examples of what are known as vertex operators. So, one of the things that I keep on harking back to is this connection with this Siegel construction, right, where you could induce the action of the affine Lee algebra, or sorry, the Heisenberg algebra to the full affine Lee algebra. This construction again relied on the on vertex operators and was categorified previously by Khovanov and Nicolle. So using this as a motivation, there was a conjecture made by Khovanov and Sussin that you could categorify this as well, right? So namely, that you can categorify that theorem. Which incidentally, this is nothing more than the mathematical formulation of the boson-fermion correspondence, which was briefly mentioned in the last talk. Great. So how do we do it? Well, we look at this and we're like, wow, that really sucks. That was awful. How on earth do you like categorify exponentials? I don't know. But we can do something else. We can rewrite our vertex operators so that they make a little bit more sense and don't look quite so horrible, or at least scary.
So Nicolle, I
Yes.
missed it. The psi without the index are the generating series of the psi with the indices, right?
Yes. So I'm gonna. That's exactly. I'm gonna specify that right now. Yeah. So one of the things that you first note is exactly what Andrea was asking me, right? So this is known as a fermionic field. If you know what that means, great. If you don't worry about it. And you can write this in the following way, right? Where these are known as the modes of your vertex operator, or the modes of your field. But then on the other hand, you look at that expression, you stare at it for a long time, you massage it a little bit, and you actually notice that you can rewrite it. And you can rewrite it in the following way. So you can show that you can show that actually each of these pieces, psi I, when you act on your random symmetric functions, let's call it f, can be written in the following way. So t to the c plus 1 times the sum of f. And likewise, you can have the analogous for the z of z. These, when you have these minus I to z, and again, you can show that locally these things are going to act in the following way. So we should get to the c minus 1. n minus 1 equals C. Okay. So what is this saying? Well, first of all, my action is local, right? It's defined on each of these graded pieces. So in order to find out what this thing is doing globally, I'm just going to focus on each of the pieces and maybe categorify the individual pieces first. So if I just look at each little piece, at each mode here, and inspect what it's doing on every piece of, or just an arbitrary element f in, some piece of my bosonic Fock space, or fermionic Fock space, sorry, I find that it acts in this way. And this looks, when you first look at it, a little bit weird, right? All right, we changed generators, which is great because we know how to categorify these. We don't know how to categorify the alphas, but it turns out that these have a very nice name. These are known, if we write it like this, as I minus C plus 1. These are known as Bernstein operators. Right, and this, the analogous thing here, is just the start version of it. If you've ever heard of them, well, if you've never heard of them, then let me suffice it to say that they show up all over in the theory of symmetric functions because they're creation and annihilation operators essentially for short functions. So for that point of view, it's actually very nice and very natural that they show up. So our first step is to actually categorify this and then enlarge the structure so that we can include the grading into it somehow. Cool. So how do we do this? Well, we do the following. So recall that when I defined the split growth and deep ring, one of the things that I mentioned is that homological shifts correspond to signs, plus or minus signs, right? So if we want to somehow encode these alternating signs, the natural thing is that we're going to lift this to a chain complex. So rather than working, so we need to pass from our category to the homogeneous category of H, right? In our object, BA, right, where A is just going to be whatever my indexing, whatever I'm summing over on this side, is going to live to a chain complex. Namely, it's going to live to the obvious thing, right, where the P's, oh, I didn't mention this, but I guess I thought it was obvious, right? In our categorification, when you take the equivalence class of the objects, the P's are going to correspond to the P's, the Q's are going to descend to the Q's with the appropriate indexing, right? So here, if we just look at this, for example, here, the P to the N should naturally correspond to P to the N. The Q to the 1M corresponds naturally to Q to the 1M. And then you construct a chain complex in this stupid way, right? N minus 1, Q, 1, N minus 1, and so on. And then you do the analogous story for BA star. Right, so this is 1, and M. Instead we go up. And so, what's the first thing you should ask yourself is, well, why isn't this stupid, right? No, really, I mean, okay, you lifted some objects, sure, it decategorifies to the same thing, but you can categorify a lot of things and do say nothing, right? So the first indication that this is actually not stupid, maybe is interesting, is the fact that I can put some non-trivial differential on here. Because I could just as well put a differential that's equal to 0, and it would still decategorify to this, okay, big thing. So what's the differential that I place here? Let's call this D and D star. Well, it's nothing more than the most obvious thing on the universe. And the magical thing is that it actually works, right? So we're going to set D to just say, all right, I have n boxes here. I have n, let's say, shaded boxes here. Let's do something like that. My differential is precisely taking one of my strands and just bending it downward, an adjunction, right? My D star is going to be the exact same thing, but instead, I'm going to be doing this. So the opposite direction. And I bet you I got the arrows backwards. Yes. Of course I did. There we go. So the first question is, why is this 0? Right? Why is D squared 0? And that simply follows from the fact that if you have any white box connected to a black box by more than 2 strands, that's automatically 0, right? That's equivalent to saying that symmetrizers and anti-symmetrizers kill each other, right? In the group algebra, the symmetric group. So a lot of the structure just naturally carries through, right? So this is actually really nice. Why? Because as they pointed out a little bit earlier, right, this is not by all means the only categorification of a Heisenberg category or a Heisenberg algebra. There are many of them. But one of the relations that pretty much is always true is this. This is always true. So these are chain complexes that make sense in any Heisenberg category, not just Khovanov's. Cool. So with that in hand, we actually have some very nice theorems that follow from this construction. Namely,
You're saying this is an exact sequence?
am I saying this is an exact sequence? This?
Yeah.
No, this is not an exact, this is just a chain complex.
Yeah.
So it's an infinite chain complex.
No, I understand. I'm just asking you what homology.
Oh, this Khovanov's Heisenberg category is not abelian. So it's just additive, so I can't take homology on this, right? It's really just a chain complex. Yeah, there's not, that question in this context doesn't actually make sense. Okay, so how do we encode in the last 5 minutes, I guess, this grading component, right? What do we do? Well, if you look at this, you realize that the grading bit is really just kind of artificial. It's not doing much of anything, right? It's just saying, it's just saying, if I start at some level C, I'm just gonna bump you up to the next level C plus 1. And that's really all you're doing, right? Most of the core of the action is really just taking place on these Bernstein operators. So if I know how the Bernstein operators are acting, then I can define the full action. And that's precisely why, to actually lift the full psi i's, you don't do anything too crazy, but rather you do the most stupid and obvious thing. You define them as a matrix. A matrix has entries on one of the off diagonals, a 0 everywhere, and that naturally takes care of the fact that you're just getting bumped up and down on your lattice, right? So then you define the psi I to be precisely an infinite dimensional matrix where you have zeros on all the diagonals, on the main diagonal, and then on the top or bottom, I always get this backwards. On the bottom diagonal, we define this to be I minus C, I minus C minus 1, I minus C plus 1, right? Each of these are themselves the chain complexes that are defined here, right? Zeros everywhere else. The fact that this is acting on the Fleur off diagonal, basically, like I mentioned, takes care of the fact that you're always going to be bumped up, right? You'll notice the indexing, bumped up in the lattice that you're acting on. And then likewise, you define psi I star to be the analogous story, right? These are infinite matrices, but instead, on the top diagonal, you define the opposite, right? You define it with the adjoint operators, right? Equals whatever. Minus C minus 1 minus C plus 1. And zeros everywhere else.
You shouldn't go the other way with the pluses and minuses as you go down the diagonal because the C.
No, because so it's a matter of
because
convention.
above diagonal.
Whether
versus
like
below.
how are you defining, how are you indexing? Are you indexing I minus 1, I plus 1, or I minus 1? Yeah. It doesn't actually matter.
Sorry, so can I try to understand what this matrices mean? So
Yes.
Are they is this acting naturally on some category, and then these are the entries?
Yes, sorry. Yeah. So what is our fermionic Fock space, right? It's nothing more than just taking a bunch of copies of CSN, of KSN, of SN modules. Right? And what I want is basically like a giant direct sum of this.
Okay, just vertex.
And so you just basically take it in a stupid way of define it to be a vector, where all but finitely many entries are 0 or non-zero rather, and then you define the action to be matrix multiplication, right? But the action which is local is really just given by the action of these chain complexes on these modules, right? And that just follows from Khovanov's Heisenberg category. Great. So given this, we have the following theorem. I have one more minute to just write the theorem. Okay. Namely, psi and psi star satisfy categorical analogs of the Clifford algebra relations, i.e., they induce a categorical action of CL on categorical Fock space. Right? And essentially, what those relations would look like is a relation that I wrote before, right? For example, this. Relations like this are lifted at the level of the chain complexes to homotopy equivalences, right? So you end up with something like the tensor product of these chain complexes is isomorphic to taking the tensor product in the opposite direction, modulo some grading shifts, homological grading shifts that have to do with the parity of I and J, right? A relation, for example, like this, right? One of the relations lifts categorically to two distinguished triangles, actually. So you end up with this and the opposite being distinguished triangles.
And who proved this theorem?
Well, that was me. Right. There you go. Okay, so this is essentially a proof of the conjecture that Khovanov and Sesson did, right? Or conjectured, and it just is categorifying the theorem by Cox. God, I'll get there. That's what I'm going to practice. Okay, great. Cool. So then, just a closing remark. One of the things that people often ask me is, well, does this categorify the Clifford algebra, right? I started the story by telling you we have this entire categorification of the Heisenberg algebra. Is this a categorification of the Clifford algebra? No, right? Or at least it depends on who you ask. If what you're searching for is not just the objects, but the actual fuller story of categorization, right? The morphisms, the structure that comes in, this doesn't give us to us. It gives us precisely what objects we would want, so they're great candidates. But for full categorification, we would want to actually know what the endomorphism algebra of these psi i's is, right? We would want to know, just like in the Heisenberg category, we had these diagrams, these morphisms that had all this extra structure. That's the sort of, I guess, conditions, the sort of information that we would want to fully construct a category here. Unfortunately, it turns out Khovanov Heisenberg category is not graded. It's only filtered. It's not Kroll Schmidt. It has surprisingly little structure to work with, so that it ends up being constructing the actual endomorphism lines is very non-trivial. But maybe we'll get there someday. Cool. Thank you.
Any questions?
So, like a question about Khovanov Heisenberg category. So you said that endomorphisms are basically like the chain algebras with
For the upward pointing strands. Yes.
Yeah.
Yes.
Is there some version of this, some other version of this categorization which has non-degenerated ahas, but like usual algebra as endomorphism?
I don't know. Yeah. there's a lot. I mean, yeah, I don't know. That's sorry.
There is.
Is there?
Yeah.
Is it just the Q deformed one? Okay. Okay. That's what I suspected that would. Yeah. Yeah. So there's a version of this category of Khovanov's Heisenberg category where instead of using the ring of symmetric functions, so SN modules, right? You use the Hecke algebra, and then you end up with a Q deformation of everything. And I think that's precisely the one that, which would make sense.
Yeah.
Of course. Yeah.
Other questions?
Yeah, so kind of going back to what you were mentioning at the beginning of the talk, you can embed sort of lots of primary algebras into this
Yes.
and so can you somehow recover the categorification figure as sort of an experimental object?
Do you mean like going backwards?
Yeah.
Yeah.
It's
So
simply what to do with the
yeah. So this is only half of the story, right? So I mentioned briefly that this theorem is the boson-fermion correspondence, right? And it's basically saying you have some Fock space, you have an action of the Heisenberg algebra, you have an action of your Clifford algebra, and the point is that you don't just go one way. This correspondence goes the other way, right? You can recover the action of the Heisenberg algebra from the Clifford algebra. In this story, using this, we don't know enough about the structure on this side to go backwards, right? So what this is basically doing fermionization, so if you do bosonization, which is the reverse direction, there is some work on it. It's due to Yin Tian. And I think he uses contact topology or something to go backwards. Right, so he defines a Clifford category and then tries to do the boson-fermion correspondence the other way. Yeah. But that's the only case I know of it going the other direction.